Hi, I'm Bethany Goldblum. Welcome to the NSSC Virtual Learning Series. So it's my great pleasure to welcome Zoe Gastelum from Sandia National Laboratories to this session. The Virtual Learning Series has been a way for us to continue to connect members of the NSSC community to subject matter experts from our partner laboratories. And so it's really nice to be able to hear from Zoe and hear about the work that's going on at Sandia. So today we're going to learn about examining the cognitive impacts of errors from deep learning systems for international nuclear safeguards verification. And Zoe's a member of the principal, or a principal member, I should say, of the technical staff at Sandia. And prior to that, she spent several years at Pacific Northwest National Laboratory. She was also co-PI on the very successful Defense Nuclear Nonproliferation R&D funded Interdependent Networks project. And she is involved in the community in a number of different ways. She's a co-chair for INMM working groups, and she's also previously worked at the IAEA. So Zoe brings a lot of expertise, and it's just a great opportunity to have you here with us today. So thank you so much, and over to you.
Well, thank you very much for the invitation. It's great to be here with you all today. I wish I was actually with you in Berkeley. When Bethany and I were doing some work together a few years ago, I got to visit several times a year and really enjoyed hanging out on Shattuck Ave. So best wishes from Albuquerque. But I really appreciate this invitation to talk to you today about some work that we're doing on some internally funded projects here at Sandia National Laboratories, looking at cognitive impacts of errors from deep learning systems, and especially as that applies to international nuclear safeguards, which is my personal favorite topic. So I will share some slides with you all. I'm not very good at monitoring chat at the same time as maintaining a coherent line of thought. So if you have questions, feel free to put them in the chat, but I can address them at the end. If you have something really burning, feel free to unmute and chime in, but I probably will not be getting to those chat questions if we're gonna make it through this in an hour. So thanks again, everyone, for joining. Before getting really into this, I wanted to just introduce you to the research team. So like Bethany said, I'm Zoe Gastelum. I'm the PI on this project, principal investigator, which means I lead the work. And my area of research is international nuclear safeguards, especially data analytics applied to safeguards verification activities. But I'm working with just a phenomenal group of cognitive scientists at Sandia. Before joining Sandia, I didn't know that psychologists worked at national labs, but we've just got an awesome team here. So Laura Matson and Mallory Stites have been the principal cognitive scientists that I've worked with on this project, but we've also had support from Aaron Jones, Michael Trumbo, and Bree Howell, who is a graduate student studying cognitive psychology. We've also really benefited from some expert consultations with other SMEs at the labs, specifically folks working in the deep learning area where they're developing algorithms and solutions using deep learning and machine learning. So those folks are Timothy Shedd, who was also part of the Interdependent Networks project that Bethany mentioned, and Michael Smith. So deep learning performance is getting much better on a number of different domains and topics. In this example, that's from the computer vision world, this shows the performance of models that are trying to classify images based on the ImageNet competitions. We saw around 2015 that performance of algorithms was actually starting to exceed performance of real life humans, which is pretty exciting. And that's led a lot of different domains to start examining deep learning as a way that they could, as a way that they could potentially decrease the workload and the burden that they have from so much information. One of those areas that's been examining deep learning and its potential for application in their area is international nuclear safeguards. And I know this is a stand-up group of folks that are on this call, but just for anyone who's not familiar with safeguards, these are a set of measures that are applied by the International Atomic Energy Agency, which is an organization that's part of the United Nations system, to ensure that states aren't misusing their peaceful nuclear energy programs to develop weapons programs. And so countries sign agreements with the IAEA that describe how those different measures and activities will take place in their country at their nuclear facilities. So the IAEA has been interested in looking more closely at deep learning. And I just wanted to share this quote with you from 2018 from the former director of the IAEA, Yukiya Amano. He said that the IAEA is going to be looking at optimal use of advanced technologies to strengthen information collection and analysis. And for the IAEA, this was referring to things like sensor data coming from countries, open source data, all the different streams of information that the IAEA has access to support that safeguards verification. So there are three areas that I think are really exciting. There are probably more, but these are the three that I'm most familiar with, where research and development is currently ongoing to look at how deep learning could potentially support safeguards verification activities. The first one is in the review of surveillance data. So the IAEA has big surveillance cameras that they put in nuclear facilities as a measure to ensure that seals aren't broken, things that are supposed to stay closed, containers that are supposed to be, in one place aren't moving around. And so at these nuclear facilities, inspectors go and they review all of the footage from, between the last time they visited to present. That can be months worth of data. And some of these cameras are taking images up to 1 image per second. So the volume of data that they have to review can be quite large. They do have some very basic support for reviewing that data right now, but not looking at things like object detection, object tracking. So there's some research happening now that's led by Brookhaven National Laboratory in New York, that's being done in collaboration with some researchers here at Sandia, where they're looking both at object detection in nuclear facilities from the surveillance data, so finding containers or equipment that are relevant for safeguards. And there's also some new work coming out looking at anomaly detection, in which algorithms are learning kind of the normal pattern of behavior at these facilities and then able to identify when, for example, containers are moving in the wrong direction or in part of a facility that they're not normally seen. Another area of really interesting research is in sensor integration across facilities. This research is being led by my colleague Nathan Showman and Ben Sapedi, where they're applying machine learning models to simulated data coming from a hypothetical nuclear facility and integrating all of that data together to make better decisions about if nuclear material has been diverted or not. Currently, this is done on a sensor by sensor basis. And so their novel approach is how to integrate that data to look for these more facility-wide patterns. And the final area that I wanted to discuss was in open source information collection and analysis. So similar to what you might see in the intelligence community, international safeguards analysts look through open sources of information such as research publications, news media, social media, websites to try to find information about the status of nuclear activities in a country and even their plans for nuclear activities, where their research might be leading them in their nuclear programs. And there's some great research coming out of Lawrence Livermore National Laboratory, where they were using deep learning models to have advanced information retrieval. So for example, you could search their tool with, for example, an image of a uranium centrifuge and bring back videos, news articles, audio clips, and they had all the different concatenations of being able to search on one type of media and bring back other types of media. So, so the only area of research from these three that's currently being very seriously considered by the IAEA is the surveillance data activities. That's being now jointly pursued with the IAEA, so they're considering how that might really be implemented. But any three of these are kind of realistic examples of how the IAEA could potentially use deep learning to support safeguards verification activities. But even the best deep learning models are sometimes wrong. There's always, that 0.001% of incorrect answers that they could give, even when they're getting very good. So, so you see here examples of, how algorithms might give really obvious wrong answers, telling this older gentleman that he's pregnant and this young woman who's obviously pregnant that she's not pregnant. But in a medical setting like that, maybe it's an error that humans can correct quite easily. But when we're talking about application to international safeguards, when there's so much technical and also political context to the decisions that the IAEA is making about these countries and whether or not they're in compliance, if a deep learning system was to, for example, identify an anomaly in a state, that would then require they have additional inspections be conducted to ameliorate that situation. Those countries might think that the system is biased against them, or that errors are causing them additional effort or burden from their safeguards agreement. And so you have to think about how it could impact both users of the system and that broader implication of what happens when these systems are giving wrong answers. So before I get too deeper, I wanted to talk to you a little bit about humans and how we're interacting with humans in our research. So, so in my view, at least, I think that there are three levels of performance that need to be considered when we're talking about new algorithms or new models, especially when they're being applied to a high consequence area like nuclear nonproliferation. So the first area is model performance, then comes signature performance, and finally user performance. And I'll talk about each of these in turn. So model performance is really looking at how good is my algorithm at detecting a defined signature. So in the work that we were doing with Bethany a few years ago, we developed a model that was looking for nuclear cooling towers, or at least this very iconic hyperboloid shaped tower that kind of symbolizes nuclear power in many places. So we were looking both for these hyperboloid cooling towers and also trying to determine if there was a steam plume associated with them, so we could make a guess about whether the plant was operating or not. So we were looking at things like, can we identify things that are not cooling towers? How well can we identify cooling towers? And then how well can we identify those cooling towers with steam? And our model did pretty well. We got, I think, in the mid-90s range of accuracy for that model. But then the question is, so how well is our signature performing? So how good is that signature of cooling tower plus steam plume actually doing at predicting operational status of nuclear facilities? So to look at our signature performance, we looked at images of cooling towers that were geolocated within the United States and compared the predictions from our model, which is, if we had a cooling tower and if we had a steam plume, with operational data that was published by the US government that was monitoring nuclear power production in the United States on a daily basis. And so by doing that, we actually decreased the performance of our overall system. Not every time that we saw a cooling tower and a steam plume, did that mean that the facility was operating? And also sometimes it was operating when we didn't see a steam plume based on those images. That could be an artifact of if the image was misdated, or if it was an image taken of an existing photograph, for example. Also things like environmental conditions. So we're not exactly sure why that signature wasn't 100% predictive, but we have a few guesses. So that decreases our performance a little bit. But then we have to think about user performance. So that is, once I give this data to my human, my analyst, how good are they at being able to understand and act upon that information, which is the model's identification of a signature that may or may not be faulty. So you have two layers of potential incorrect information coming into a person who then has to make a decision about, was this plant operational today or not? And that's where our research is really focusing, is on that human aspect of how is a human interacting with data that's output from a machine learning or deep learning model. So, we are, let me go back to this slide. So we are doing human performance testing in this research. So in non-coronavirus times, we would be bringing people into the lab, which you can see an image of here with my colleague Laura sitting at the console, where we would be measuring reaction times of experimental participants to data stimuli. Also their accuracy in those reactions, and we have equipment that can monitor eye movement, so we can track what part of the information that we're presenting is the user actually focusing on. Because we are so remote right now, we're actually conducting these experiments over Amazon's Mechanical Turk, and through that we're collecting accuracy and response time measurements, but we're not doing eye tracking right now. We have some plans later on this year to start collecting some additional data, but it'll depend on how close people are able to be in these small spaces like our laboratory. So, so we started this research looking at domain general data. So on the left-hand side, you see kind of this typical data set from the cognitive psychology community, in which it's a bunch of T's and almost perfect T's that aren't quite perfectly aligned on a clouded background. It's a visual search task. So the users to this, these general types of tasks are trying to find the perfect T, which, if you can see my pointer, is right here in the top left part of the image. That gives us some really interesting information about kind of generally how people are using machine learning outputs for visual search. But we wanted to go a step further and use some actually safeguards relevant data sets and do some trials with that also. So this year, we're just starting to do some experimental testing with a data set of nuclear cooling tower and related images, in which our participants are doing an identification task. So trying to determine if the image contains a nuclear cooling tower or not. So there are 3 experimental findings that I want to share with you today. And one is our very first finding of this study, which was that on-stimulus visualizations were more effective communicating information to our users than off-stimulus visualizations. So what do I mean by that? In our studies using this T's and L's psychology stimuli, we had 6 different types of visualization that we showed to our users. The top left here is with no machine learning aid at all. And I should say, actually, before I go further, that there's actually no real machine learning in this experiment at all. We're using simulated machine learning outputs so that we can experimentally control how the data is presented. So in this top left image, there's no support from a hypothetical machine learning algorithm. In this top middle, there's a blue bounding box around the T. On this top right, we used what in the deep learning community is called the segmentation mask to highlight the perfect T. On the bottom left is a heat map showing probabilistically where that T is in the image. Here is, so the first three that I spoke about that don't include the no aid condition, the bounding box, the segmentation mask, and the heat map all represent those on stimulus conditions. And then we had two conditions where information was provided to users on the sidelines of their screen. So here in the bottom middle, we showed a histogram to users that basically communicated the same information as the heat map, but was not applied directly on top of the stimulus. And finally, in the bottom right, we showed some textual clues about where that T was located. So it says here, the target is in the top left quadrant. We showed our participants these different visualizations with several different types of simulated output from machine learning model responses. So in the correct response category, there were true positives in which there is a perfect T in an image and the algorithm detects and correctly places that the indicator around the T. And in a true negative is when there's no target, there's no perfect T in the image, and our model says, yep, there's nothing here, and it doesn't show an actual indicator of where something might be. In terms of incorrect responses, and this is the part that's most interesting for me, we had three types of incorrect responses that we showed. The first was a false positive. So this is a false alarm in which there's no target in the image, but the algorithm shows, basically selects a distracting item. So either an imperfect T, which we call an L for simplicity, or even maybe like some background of that cloudy area. There's a false negative where there is a target in the image, but the model just misses it and says that there's no target there. And finally, we had a condition in which there is a target, but the model selects an incorrect distractor. And we call this a false positive plus a false negative. So there's a target present, but the model is selecting a distractor instead. So we counterbalanced the visualizations across these different response types. And what we found was that for the visualizations that were provided directly on the stimulus, so the bounding box, the heat map, and the segmentation mask, our participant accuracy was actually either very close to or above that no aid condition. So the machine learning was helping them find the right answers. For the off stimulus visualizations, we found that the participants there were doing either about the same or slightly worse than in the no aid condition. So when they were having to look away from the image to find that output from the model, their performance was actually decreasing. And we saw a similar trend in their response time, where those on stimulus visualizations were helping the participants more quickly find the answer, and the off stimulus were taking much longer. So that was our first round of results, and we used that to inform how we provided visualizations to our participants in all of the following studies. So in this second finding, we observed that even deep learning that had very poor performance was better than having no deep learning at all. And there's a caveat to this. So it's most of the time it's better, and I'll explain what that means. So here we're looking at participant accuracy when the model provided correct answers. And the human accuracy with no machine learning aid is delineated with this blue line. It's in two different places because our participants were better at identifying images that didn't have a T than they were at identifying images that did have a T. And it's because the T is kind of hard to find with that cloudy background. So, so for images that don't have a T, when the model provided the correct answer, there's no T in this image. participants were performing about as well as they did with no aid, which makes sense because for most of those conditions where the model didn't identify a target, there wasn't actually a stimulus presented to the users. For this condition where there was a target present and the model correctly identified it, we saw our participant accuracy go up from 74% to over 90%. So a really big jump in human performance when they had that help from an algorithm saying, hey, you know, the target's right over here. Now, what happens then when the model provides a wrong answer? So let's start first with false positives. So when the model incorrectly identifies a distractor item, something that is not a perfect T, and says, here's your target, performance stayed about the same as it was with no aid. So people were able to look at that and say, yeah, that's not a target. I don't see one in this image. With the false negatives, this is when there is a target, but the model's not identifying it. Again, people had about the same performance as they did without that aid at all. Again, because in this condition, they weren't being shown any information by the model. But this most interesting one for my team was this false negative plus false positive condition. So this is where the model, again, is selecting a distractor target, but there is a correct target within that image. That actually caused people to have worse performance than if they had no help at all. So their performance here went down from 74% with no aid to about 68% when the model was telling them the wrong item as being the target. So that for us was really interesting in terms of thinking about how we might adjust thresholds for decision making in these models to try to decrease this type of error as much as possible. So the third research finding that I wanted to share with you is that as deep learning performance goes up, user performance also goes up most of the time. But again, there are some really interesting examples of when human performance is getting worse. And for me, that's those are the real gems of the research findings. So, so this plot just shows how human accuracy on our task increases along the y-axis as our model performance increases along the x-axis. So we showed participants several different accuracies of models between 50 and 95%. And what we saw was that the models were helping them and helping them more and more as the models improved, so did our user performance. When those models were providing correct answers, either with a true negative that there's no target or true positive correctly identifying the target, we see in this left-hand chart that our human performance is right at ceiling. Users were doing very, very well when given correct information. However, when the models were giving wrong information to users, again, we see some human performance metrics dropping below their anticipated performance with no aid. So both the false negative condition in which the model is missing a target and that combined false negative plus false positive where the model is identifying an incorrect target but a correct target is present, those two yielded across the spectrum of our model performances, performance much below anticipated human performance on those activities without aid. And then we saw in our false positives that as we increased performance of our models, in the early stages when the models were very poor, we saw that users probably were not trusting that model very much and they were making their own assessments and still had very good performance. as those models got better and better, and we can see a change here kind of between 80 and 90%, is where perhaps our participants were over trusting the models and they were becoming less and less able to recognize when those models were making mistakes and then correct for them. So even though their overall performance on the task is increasing, they're less able to recognize those mistakes from deep learning. So, that's our latest and greatest in terms of our results. We just finished a data collection this week that was looking at confidence metrics as applied to these types of models. So again, using the bounding boxes that you saw before, we started putting these confidence metrics. And if you're working a lot with deep learning, you may have seen these before, where sometimes it's listed as probability of a target. It's not really a true metric of probability, but it can be interpreted as like confidence of the model that the target is within the given space. And we wanted to see what happens to our users when we manipulate those. So when the output of a deep learning model is correct, like in this bounding box that highlights the T on the left, and it has a high probability, is that going to impact our users differently than the same bounding box around the same T with a lower probability? And again, what's really of high interest to my team is what happens then when we start manipulating that data so that the machine learning output becomes more and more incorrect. So for example, very high confidence ratings on incorrect identifications of distractor items. So we should have results of that study very soon. Within the next few weeks, we anticipate having initial analysis of that data. So I hope to be able to follow back with you soon to provide you with that information. We're also about to launch some studies that look at impacts of different error types and also the ratios of those error types. So in some of the previous results, we noticed that when in conditions where the deep learning algorithm was missing a target, either as a false negative or that false negative plus false positive condition, these were seen as like the most detrimental to human performance as compared to performance without any aid from a deep learning algorithm. So in these experiments, we're going to dig in more deeply to see how we can manipulate those types of errors that users are seeing from the algorithm, to see how this might impact, for example, if they're just getting those false positives, just getting those false negatives, or also manipulating the ratios in which they're seeing those errors, given a constant model accuracy rate. We're also really interested in looking at explainability measures such as salience maps. So this is actually, this is an example again from the Interdependent Networks project that Bethany mentioned, in which our model always was predicting this gentleman in the striped shirt as being a cooling tower. So we tried, several different models that had very good performances at identifying cooling towers, and this person just kept getting identified over and over again as a cooling tower. So we ended up running some explainability measures over our results, and we see here that maybe his neck is, a little bit shaped more like a rounded cooling tower edge. But that gave us some information about how we might provide additional training data to our models. But we're really interested in this study to see about what happens when we have, good explainability, kind of realistic explanations for why a model is wrong, compared to really unintuitive ones to a user. And so those are our plans for the explainability. It turns out that this person actually is a cooling tower. He's a member of the cooling towers band, but our algorithm was not trained on identifying that type of cooling tower. And the final area that we're going to be looking into is model transparency. And this is really trying to get at how much information we're providing to users about the model, such as the data that it was trained on, where the algorithm architecture came from. So just as an example here, two kind of common types of algorithms that are floating around in the deep learning world, especially for image classification and object detection. Some are coming from TensorFlow, which is a Google Brain developed set of libraries, very highly regarded. They have big professional conferences every year, lots of tutorials and information on the web. And on the other side, we have YOLO, which is the you only look once algorithm. This is, I would say, one of the most commonly used object detection algorithms that's being circulated in this world today. But when you look at the provenance of the algorithm, the developer, Redmond, has a really eccentric resume. So these My Little Ponies are straight from his resume. So this is asking, given this information about these models, which one are you going to trust more? One that's developed by Google or one that's developed by this person who really has an affinity for My Little Pony? So what we hope to do with this work ultimately is to inform deep learning developers and those who are adopting deep learning models about how to balance model performance and user performance. We anticipate that our results from this research are going to be able to better inform developers about how good their models really need to be. At a certain point, if they can stop trying to get that extra 0.001% on their precision or recall scores, to determine, what level is good enough for human users. In some cases, it may even be that model performance should be a little bit lower to support users, but also make sure that they're staying engaged and not developing that over trust of models in which they're just accepting any model recommendation. We're also hoping to be able to understand how much information we should give to users about the models that they're interacting with. I would say that within the deep learning development kind of R&D community, there's a lot of excitement about providing a lot of information to users about the different hyperparameters that were used in these models. Our hypothesis is that for typical users or analysts who maybe don't have computer science degrees, that might not be quite as relevant for them. And so overall, just trying to use this information to enhance the user algorithm systems. And again, for the world of international safeguards, we think this is really important because the decisions that are coming out of international nuclear safeguards and analytical processes are being viewed by the entire global community, especially those interested in nuclear nonproliferation. They help countries determine their own sense of security. Some countries might make their own decisions about if it's relevant for them to develop nuclear weapons programs or not based on these decisions. It's causing or potentially relieving burden on nuclear industries within countries as they have to experience more or less engagement with IAEA inspectors tramping through their facilities. So there's so much that goes into these that we're hoping we can really shape the conversation before these algorithms are fully implemented within this context to help basically make the system as robust as possible, given the potential for errors, again, even from the best performing models, or perhaps from models that have been subject to adversarial machine learning or some sort of correction. So with that, I will just put this onto my last slide. This is my contact information in case anybody wants to follow up online, or if we don't get to your questions today. But otherwise, I think we have some time for questions. I'd love to hear what you have to ask. Thanks.
Thanks, Zoe. That was an excellent talk and really interesting. It's nice to see the evolution of the work following interdependent networks. So normally the way that we, and I failed to say this at the beginning of the session, but normally what we do is folks enter their questions in the chat box. But I think we have, since we're not using the webinar format today, that it's fine if people just want to speak up and raise their questions. So either way, if you want to put your question into the chat, then I can pose those to Zoe, or if you prefer to unmute, that's fine too.
So one thing that I'll just start talking while people are thinking about their questions. One thing that I can tell you about research in this area of nuclear security and non-proliferation, since that's this crew, is that before I became a professional in this area, I really didn't understand how interdisciplinary it was. So so I'm a political scientist by training. I work with computer scientists and nuclear engineers and mathematicians and graphic artists. So it's been really exciting for me to see kind of the growth within the nuclear security community of all these different domains coming together. I've seen that quite a bit, especially in the NSSC program, you know, where you've got folks coming in from different parts of the university. So it's great to see what's going on at Berkeley and elsewhere, where people are really kind of embracing that multidisciplinary approach to some of this research. Because I mean, I couldn't do the experimental psychology that we're doing on my own, and you know, it's just great to see how folks are starting to work together more and more across many different domains.
Hey, Zoe, this is Karen Hogue from SNL. Hi, I have a quick question for you about, you know, I think it makes a lot of sense, and you had a lot of great examples of how to apply, well, how it might impact when you still have an analyst who's looking at the data and, you know, like satellite imagery analysis or that sort of stuff. But what about, how would you apply any of your findings or your work to situations where there might need to be information barriers, such that, you know, there's the data coming from the sensors isn't coming in as data, it's being integrated, something similar to the second example that you gave of where there's kind of this integrated from multiple sensors type situation. Is there any kind of lesson learned or application of kind of that threshold that you're looking at that would apply to situations with information barriers?
Yeah, Karen, that's a great question. I love it when people who really you're so deep in this also that it's really fun to have these conversations. So so my understanding of the approach that's being taken for safeguards to integrate deep learning is that you know, an algorithm will never be the final say in an outcome for a country's safeguards conclusion, for example. So in the facility sensor integration example, even if all of that data isn't available to IAEA inspectors, it could be that that the algorithm can indicate a certain timestamp that needs to be checked at various points within the facility, or an area, without disclosing that facility data directly. Within your question, that seems like it's maybe going more towards the information barrier scenario, where you would get kind of like red light or green light type answers. That, I mean, to me, that's a whole new level of tricky, because that removes the human a little bit more from the decision-making process. We haven't looked too much at at how you would kind of remove humans one further step to use that type of information. Because the information at that point is so cut and dry that it's almost as if the human is cut out.
Right.
So we're really most interested in, like how do we handle it when there's like some level of detail that can be provided to the human. If an information barrier is giving a red light instead of a green light, I think the most you can probably do is measure again. Or recalibrate your equipment. But it's a great question. I'll take that back to my cognitive psychologist and see if they have any further comments on that. I'll get back to you over email.
No, that's great. Thank you, Zoe. I appreciate it. And I'm almost thinking if it's something more, I mean, to your point, it's not necessarily changing the way that they're interacting with that, yes, no, red light, green light, but it's almost the way that they're then internalizing that and combining it with the broader picture of looking at a state and looking at the fuel cycle and like almost like the broader analysis and whether or not how that's biasing almost, I guess. So.
And that's a fascinating area too of how that information can bias people, even if they realize that it's incorrect later on. There's just some fascinating research going on within the academic world about bias and information, like coming from kind of like the fake news, I guess. Once people are seeing deep fake videos or like rumors on the internet, that information is spreading so quickly, whereas like the corrections to that information are much more slow to disseminate across social networks. That it's there's a very important bias part of that, where even if the red light was wrong later on and that the green light should have been right, how do you it's really hard for you to unsee that red light in your mind. That's a great point.
Thanks so much, Zoe.
Thanks, Karen. Good to see you.
And another question, Zoe. So you highlighted the difference between, I think you called it model prediction and signature prediction. So what do you see as kind of the next steps for, or how best do you see linking the model prediction to the signature prediction? Do you feel that this has to be approached through physics-based kind of ab initio calculations of how those connect in order to apply these types of methods in a safeguards context, or is there another way? And if so, what?
Yeah, that's a fantastic point, Bethany. So yeah, I would argue that that the signatures should be vetted and validated with with the appropriate physics. But then when we then develop a model to try to predict that signature, we need to like appropriately discount how predictive is the signature and how predictive is our model then of that signature. And then, then our argument really is, what can a human do when they have that answer? But absolutely, you can have the best model and your top analyst, but if your signature isn't completely right on the mark, then you've got to account for that in terms of your overall system performance.
Thank you for a great talk, first of all. My question is, do you think these results would hold if the classification task were more complicated? Like it's pretty easy to look at that image, and if you look at it for longer than 5 minutes, you can probably figure out exactly where the correct T is. But do you think for a task that's a little bit more complicated, would these results hold, or like how would the difficulty of the task affect the experiment?
Yeah, and that's I think that's a really relevant question. So it's why we're starting to move into the domain relevant images that we're going to be using with the cooling towers. But again, this type of study has been translated to different fields like satellite and SAR imagery. They use a really similar test with TSA agents who are, looking through your luggage with X-rays. So it's so the task is really defined to be appropriate and generalizable to a lot of different types of visual search. But I absolutely agree. I mean, given enough time, humans can do really well on these things. The one aspect that we haven't really been able to touch that I'd really like to get into if we have enough time later this year is the prevalence of targets. So for example, in our images that we showed to participants, I think we had targets in about 2/3 of them. There have been studies with the same data set where only a single participant is presented with 1,000 of these. It's a 2-hour test, and only the very last image has that T. And there's some great research coming out of the cognitive bias community about prevalence and how if you don't expect to see many things because your target is very rare, it's much harder to find it when it actually shows up than when it's occurring frequently. And so this is a big thing, like especially for TSA when they're looking through luggage, like they're not gonna be expecting to see really bad things going through often, but we still have to keep them prepared and active to see those. But the same thing with safeguards in that, it's not common for countries to be developing nuclear weapons programs. And so, the ones that are suspected of doing so are quite visible. But at the same time, when an analyst is working on, one of the other 180 plus countries, when I was an analyst at the IE, I was very junior, so I had like Trinidad and Tobago and Vatican City, like countries that weren't very likely to be having those signatures, then it's really important to be especially aware then of how their own attention over that prevalence task is combined with the machine learning outputs. There are stories of algorithms at like radiation portal monitors in right after the collapse of the Soviet Union that had so many false alarms that like the Russians were taking them apart and using them to dry fish instead because the false alarms were such a nuisance. And there wasn't real radioactive material coming and going from those doors. We hope. And so there's definitely there are many more areas that we still need to look into.
Thank you.
Thanks for your question.
I think we have time for one final question.
Hey, Zoe.
Hey, Chris.
So I was curious. I guess you demonstrated a way in which we can, make an importance map, so to speak, of the pixels that you showed, where the model messes up and the human is shaking their head, wondering how it got so wrong. And so I'm curious, given that a lot of the research that you've done is on how do humans screw up, if there's sort of a way to close the loop where you can have the machine and doing some sort of augmented reality assisting the human, but the human also having a feedback into the machine where they can say, okay, I think you've identified these problems wrong, and the machine is able to distill what the cases in which the human identified the thing wrong and the machine was actually correct, so that you can further refine both the model and the user's understanding of the model.
Yes, that's fantastic. And actually, so it's at least in the psychology community, they call that feedback, right? So that's letting the user know when they're wrong. But that's also a really important part of iteratively training your model to better perform on those cases that they're getting wrong. So there can be feedback from both cases, both from a human user saying the model got that wrong, and also the model saying, hey, I really am right this time. You should listen to me. And we're in kind of an ongoing debate about how many times an algorithm should be able to say, are you sure you don't accept my recommendation on this? Because there could be some cases when a user dismisses a prediction by a deep learning model that's actually correct. And we've seen that happening even among our research team as we're designing these tasks. You know, sometimes we make mistakes, and so there should certainly be a feedback loop on both ends, and then, you know, maybe as AI develops even further, some sort of conversation between an algorithm and a user where an algorithm might say like, hey, maybe just take one more look at that before you tell me I'm wrong, like just make really, really sure.
Yeah, that is a really interesting point. I think like the sky that was identified as a cooling tower too. If you do understand the kind of elements of his image that were driving his cooling tower assignment, then being able to feed back in additional similar musicians or unclear that, you know, that could help move you out of that space where you're classifying those folks in that way.
Yeah.
So we are out of time. Thank you so much, everyone, for joining today, as well as for the rich question and answer session. In the chat, I'm going to post a link to the virtual learning series. So this talk will be linked, the recording will be linked there, as well as a number of other resources. So, and thanks again, Zoe, for joining us today. I hope you all have a great rest of your day.
Take care.
Bye.
Thanks, Zoe.
Bye, Zoe.